Hey there everyone, this is the video for the exercises for section 1.2 on exponential functions, so let's jump right in. The first one is exercise 5 from the textbook. It says, these are instructions for exercises 5 through 8, that these are functions that represent either exponential growth or decay. So the questions are, what is the initial quantity? What is the growth rate? And then there's this other part, state whether it's continuous. We are ignoring that part. That will come up in a later section, so you can ignore that part for now. So first, what is the initial quantity? Well, we talked in the section about the general form for an exponential function, having the form p of t equals our starting or initial value p0 times our growth factor to the independent variable t. So what is the initial quantity? Well, it's what would normally be this p0, and that's 5. Then it says, what is the growth rate? And you might remember that there's a slight disagreement between the book's terminology for growth rate and the terminology that most of the rest of mathematicians use. The growth rate, they're talking about this general part. The book likes to subtract 1 and say that the growth rate is 7% or 0.07. It's fine either way if you say the growth rate is 7% or a 1.07 factor. Both of those are totally acceptable ways to phrase your answer. OK, now remember with these exercises, I prefer if you pause before I do the answer and try it yourself. And then once you're done, or if you get stuck, then you play and you see what the answer is. Moving on now to the second question. The instructions are to write this function in terms of that normal form that we just wrote on the last slide. So we're going to rephrase it. Now, why do we need to rephrase it? Because our usual form has an a to the t, and this is doing that thing where we transform it. It's already transformed into base e, so we want to turn it back. The question is, so that's the first part. The second part is it exponential growth or is it exponential decay? And we'll know that once we transform it. We'll look at whether a is bigger than 1 or less than 1, and that will tell us. But it's maybe a little bit hard to see at first in this form. OK, so we want the form p of t equals p0 times a to the t. And we've got that p0 part just fine. That's the 15. But we want a number to the t, and instead what we have is a number to the number times t. So we use that rule of exponents that we talked about, where a to the b times c power is the same as a to the b to the c. And that tells us that e to the 0.25t is equal to e to the 0.25, then to the t. So all that's left to do is to figure out what that quantity is. Now, I told you in the syllabus video that you won't be required to have a calculator for exams. In fact, they won't be allowed. And so obviously on an exam, I'm never going to expect you to calculate something like e to the 0.25 in your head. But the book questions and the Wiley Plus do need you to calculate quantities like that, so you should have a scientific calculator that can do it. Now, I'm going to pull up our on-screen calculator here. OK, hopefully that worked. And we're going to calculate e to the 0.25. So the way we do this on this calculator, at least, is we put in 0.25, and then we click this button that says e to the x. And it tells us that it's about 1.284. So let's make a little note. That's about 1.284 approximately. OK, so the way that we would write this as this function, if we were to write it this way exactly, meaning not using a numerical approximation like this, we would say p of t is p0, that's our 15, times e to the 0.25 to the t. Now, it looks like we haven't done anything interesting there, but having these parentheses makes it clear that we've matched the right form, because this term here, e to the 0.25, this is our a. If we were to write it approximately with this approximation, then we have 15 times 1.284 to the t. And now that we have that form, it's easy to answer the second part. Is it growth or decay? Well, that is governed by whether our exponential factor is bigger than 1 or less than 1. In this case, it's greater than 1, and so this is exponential growth. OK, that wasn't too hard. Let's take the calculator away for now and move on to question number 3. Here we've got 2 parts. They give us the form of a function. This is our general exponential form. You shouldn't be confused by the fact that they use q instead of p. These are just letters, and you can use any letter you want. Now, they're making a point here that they also want you to think about the a as being 1 plus r. Now, just to clarify what they mean, we had an example a couple slides ago where it was like 5 times 1.07 to the t, I think. They're saying you can think about that as 5 times 1 plus 0.07 to the t. And that's only just to emphasize that 1 is like your base, and then 0.07 is how much you grow. You're growing by 7%. OK, so don't be too confused by that. So here's the question. They're giving us 2 points, and they want us to find the base, a, and find the growth rate, r. OK, well, once we find a, finding r will be easy. We'll just subtract 1. Now, this is kind of like the question from 1.1 where they gave us 2 points on the line, and they said find the equation for the line. Here, they're giving us 2 points on an exponential growth curve, and they're asking us to find a. Now, even though they don't ask us to, I'm also going to show you how to find q0. And so what we're seeing is that just like 2 points determine a line, 2 points also determine an exponential growth curve if you know it's an exponential growth curve. So this is one of those questions where I didn't give you a formula in the section for exactly how to do this. And that's because this is not a class about memorization. It's a class about understanding math and graphs and calculus. So we're going to think about what we know, what we want to know, and try to figure out how to get from one to the other. So we have 2 points. Let me write this f of t again. F of t is q0 times a to the t. And we know that if you plug in 5, you get 75.94. So that means we know that 75.94 equals q0 times a to the 5. This is one piece of information. Our second piece of information is that if we plug in 7, we get 170.86. So even though you might not see yet what to do next, you see that we have 2 pieces of information, and we've written them down. Whenever you get stuck on a math problem, don't just stare at it until the answer comes to you. A lot of times that's not going to work. You're going to be staring for a long time. Just start writing stuff. And it might be wrong, it might be right, but you just got to start writing, and that will jog your brain eventually. So here we've got 2 equations, and they have 2 unknowns. They both have a q0, and they both have an a. Well, here is the part that might be a little tricky at first. You want to solve for one of these. They both have a q0. This has 5 a's. This has 7 a's. So if you think about what exponential growth means, the q0 is just the starting point. What this says is that after 5 hours, 5 days, 5 years, I have this much. And after 170, I have that much. So I'll show you how to figure this out symbolically in a second. But some intuition should tell you that what this means is that I can get to 170.86 by starting at 5 units, 5 of whatever, and multiplying by 2 of my growth factors. Because from 5 to 7, that's 2. Here's how you would come to that conclusion symbolically. If you take these 2 equations and you divide one by the other. So let's divide both sides of equation 2 by both sides of equation 1. So that tells us 170.86 over 75.94 equals q0 times a to the 7th over q0 times a to the 5th. Now, because we're dividing, the q's cancel, and we have 7 a's on the top and 5 on the bottom, so that's a squared. We're solving for a, so let's take the square root of both sides, and that tells us a is the square root of 170.86 over 75.94. Okay, let's bring up the calculator again and plug this in. So we've got, we start with 170.86 divided by 75.94. Now let me point out, if you're using a simple calculator like an app like this one or on your phone, you usually have to proceed by order of operations, where you have to, it's not smart enough to do them all together. If you're using something like Google or Wolfram Alpha, you can type these in all into one expression. OK, so that's the fraction. Now we need to do the square root. And we get about 1.4999. So let's just call that about 1.5. OK, so that means that's our first part here. A is about 1.5. Now it also says to find the percentage growth rate R. So if we look at our formula right here, R is just the growth rate minus 1. So if you have a growth rate, if you have a base of 1.5, that means you've got 50% growth. So R is, you could say, 50% or 0.5. Now the question doesn't ask us to find Q0, but let me show you how you would do that, because that might be something another question asks. What we've got right now is we found A. So let's go back to one of these points and plug in what we know now. Let's make some space. So now we know that 75.94 equals Q0 times 1.5 to the fifth. Well, this is very simple, because we know now that this is equal to the unknown times 1.5 to the fifth. That's just some constant. So let's divide it over. That tells us Q0 is 75.94 divided by 1.5 to the fifth. So let's pull up our calculator again. Let's do, I think we can do this with parentheses. So let's do 75.94 divided by, we can do an open parentheses, 1.5. We have this x to the y button, so x to the y, so 1.5 to the fifth, close parentheses. And here we go. We got about 10.00032. So we'll call that about 10. So that means that our final answer, well, it didn't ask it, but if it asked us to find both variables in the function, we would say that f of t is about 10 times 1.5 to the t. Now, if you had a calculator and you wanted to check your answers on this, this is another place where it's really easy to check your answers. Let's pull up the calculator again, and let's check that if we plug in both of these points, we actually get what we claim we get. So the first one, we plug in 10 times 1.5 to the fifth, 75.9375. Now it says 75.94. We don't have the wrong answer. That's just because we're doing these approximations here. And let's check the other point. If we do 10 times 1.5 to the seventh power, 170.859, and we were expecting 170.86. So not exactly, but close enough. Good. So we checked our answers there. Moving on now, let's go to the next problem. This one's a little bit more conceptual. It's the same kind of idea, but they didn't give us exact number. Well, they kind of did. We'll see. So here's a graph, and it says give a possible formula for the function. Now, they did not tell you that this is the graph of exponential growth, but they want you to recognize that it kind of has that shape. And since we're in the section on exponential growth, that's a reasonable assumption. We don't know it for sure. This could be any kind of wacky function, but we're going to assume exponential growth. And that means we're assuming that it has our general form, f of t equals p0 times a to the t. So let's try to do the same thing. Let's try to find p0 and try to find a. we do kind of have 2 points like before. We have 2 comma 12, and we have this y-intercept 3. So that's really 0 comma 3 and 2 comma 12. But it's a little bit simpler than the last one because we've got this y-intercept, and that's kind of exactly what p0 is. Now, if you didn't notice that, you could do the exact same thing in the last question. You'd write out the 2 equations, you'd solve for a, then you'd solve for, in this case, p0. But we can be a little bit smarter the way we do this. This is the y-intercept, and so that is our p0. So because of that, we know p0 equals 3. So to find a now, we can just think about what happens as we move from 3 to 2. We'll write the formula, but let's think about what it means intuitively for a second. This says as I go over 2, so I go from x equals 0 to 1 to 2. That wasn't to scale. Let me try that again. From 0 to 1 to 2, we go from 3 to 12. Now, what kind of factor is that going from 3 to 12? That's a multiple of 4. So we go up by 4 every time we go over by 2. So if you're growing by 4 every 2 steps, that's like growing like the square root of 4 every 1 step, and the square root of 4 is 2. Now let's see what that means in terms of, let's just calculate that same thing symbolically. Since we know this already, we can just say 12, that's our f of 2, is 3 times the unknown a squared. So we don't need a calculator for this one because we can divide the 3. That tells us 4 is a squared, and that tells us a is 2 because we're taking the square root of both sides. Now, you might remember that when you take the square root of both sides, you technically might need a plus or minus. But in this case, we know, because we're talking about exponential growth, that a has to be a positive number. So our possible formula is f of t equals 3 times 2 to the t. And there we go. So same kind of problem as the last one, but a little bit easier on the numbers, and we didn't need the calculator for it. Last problem of the day. This is a problem about exponential decay and half-life. So if you study the radioactive element, radium-226, it has a half-life of 1,620 years. So what this means is if you have radium-226, then over a very long time it kind of sheds, it radioactively decays into other things, and the amount that's left as radium-226 decays exponentially. So it goes down by a certain factor every year. In this case, after 1,620 years, it goes down by 50%. So here's the question. If you start with Q0 amount of radium, grams or whatever, explain why what's left after t years is this exponential decay. So basically, part A is saying how can you go from knowing the half-life as 1620 to getting a formula that tells you how much it decays every year. And then part B wants us to use that formula to figure out how much is left after 500 years. OK. So, and one thing that we're going to realize is that we have found here the first error in the textbook. This is actually wrong, as we'll see soon. And not only is it wrong, but you'll see how you can figure out that it's wrong. Not only will we see how to get the right answer, but if that was correct, then this would have made no sense at all. So again, this is something that even if you missed the calculation, once you did part B, you would have said, wait a minute, something's wrong here. But let's jump right into that. So what we know is the half-life is 1,620 years. I always like to kind of summarize the important information before I start, because then if I don't know what to do, I can kind of look at everything that I've written and stare at it and maybe see how some of the puzzle pieces fit together. So what does it mean for something to be a half-life? It means after that amount of time, the amount left is half of what you started with. So that tells us if I start with Q0 and I multiply by whatever my decay is, which we don't know yet, we're going to show that it's, well, it's not really this, but we're going to try to figure out what it is, to the 1620, then how much is left? Well, if that's the half-life, then how much is left is half of Q0. Q0 over 2. So this is an equation with Well, it's got two unknowns at first, right? It's got q0 and a. But let's first divide both sides by q0. So that's a 1/2 on the left and a 1 on the right is a to the 1620. And now what we have is an equation with only one variable, so we can solve for a. Now, you might have actually just arrived at this on your own without this first one, because we didn't really need q0. If you have a half-life, you could just say, assume for the moment I start with 1 of whatever, 1 gram, 1 kilogram, 1 bucketful. Then at the end of 1,620 years, I should have half a gram or half a kilogram or half a bucketful. So how do we solve for a? Well, this is where we need some roots. So we could phrase this either as the 1,620th root of 1/2. That's like not a square root, not a cube root, but a 1,620th root. The easier way to enter that in most calculators is as 1/2 to the power of 1 over 1620. That's just another way to write the same quantity. So let's figure out what that is. It's not going to be what the book says. Our calculator will help us here. I'm certainly not going to expect you to do something like this on an exam. If you did have a question on the exam, I would tell you to just leave it in this form, and then that would be your answer. But the book wants numerical answers, and so does Wiley Plus, so our calculator will be helpful. We're going to do 1/2 to the power of 1 over 1,620. OK. This looks almost like what the book says. The book says, let me move my little x so we can see again, 0.99572. But my calculator says 0.999572. So this is really, you might look at this and first and think, oh, did I make a mistake? Well, what's more likely, that you made a mistake that just happened to add an extra 9, or that the book has a little typo here? OK. So our answer is correct, and we will justify that in a minute. So I'll show you another interesting thing. So let's write this, though. This is about 0.999572. So our actual function is q, and let's write q of t, just to be clear, even though they didn't write it there, is q0 times 0.999572 to the t. OK, now part B says what percentage is left after 500 years. So let me hide the calculator for a minute. Part B, what's left after, after 500 years? OK, let's use it with what we know the correct answer is now. And then we will assume the book was correct, and we'll see how that's total nonsense. And that would have been your hint, even if you were confused, that the book must be wrong. So how much is left? This is asking really for a percentage left. So how do you figure out percentage? Well, same kind of ideas over here. You could start with q0, or you could just start with 1. Let's say I start with 1, whatever, 1 gram, 1 kilogram, 1 bucketful. So we start with 1, and we do 0.999572 to the 500. And for example, if this gives us back 0.7, that means we started with 1, we ended with 0.7, so 70% is left. OK, so our calculator, let's see if we can slide this over here. We need to do 0.999572 to the power of 500. And we get about 0.8073. So what that tells us is that our answer to part B is the amount that's left is about 80.73%. Now let's do a little bit of a sanity check. Does 80% sound like it could be in the ballpark? Well, the question tells us the half-life is 1,620. So after that many years, it should be 50%. So does it roughly make sense that after 500 years, OK, that's less than 1620, we have 80%? Yeah, that kind of makes sense. Now remember, exponential decay is shrinking the fastest at the beginning because the curve looks like this, very steep, and then as time goes, it gets shallower and shallower. So about a third of a half-life, you lose 20%. That makes sense. Now what if we had used the book's numbers? What if we did 1 times the book's growth rate of 0.99572, which is missing that 9. Now that seems like a small error. It's only an error in the thousandths place. Let's do this to the 500. The book's answer would be about, let's use a different color so we don't get confused here, about 11%, 11.7%. Now this is where, if you did this, you would hopefully think about, could that make sense? And you would realize, no, it doesn't make sense at all. A half-life is 1,620 years. That means after that long, 50% should be left. So how could it be possible that after 500, after less than a half-life, you've already lost almost 90%? So it was really helpful for the book to include part B here because it helps us catch their own error in part A. OK, so those are the 5 example exercises that I wanted to do in section 1.2. Hopefully this has helped you understand the ideas. Let me remind you at this point that these exercise videos you should think about as a required part of lecture. If you just watch the lecture videos and you skip the exercise videos, that is in no way enough practice. You should really think about these as part of the lecture. And then after you've done these, that's a good time to go to either Wiley Plus and start trying those problems, or going to the other textbook problems that we don't collect but are really important for your practice. Thanks for watching.